within your area of expertise and the specific style of quantum architecture that you've developed, what is the frontier of quantum computing and architecture?
Today's quantum computer, right, rely on analog approach. So if you look at the major quantum computer being built, they are using very, very high precision microwave pulses to manipulate the qubits, right? Qubits is the fundamental unit for quantum computer. So this approach actually worked pretty well, already gave us a very, very high. Of course, it also poses some fundamental limits from building the utility scale, or we call the larger scale, fault-tolerant quantum computers. Why? It's because using this approach, right, we have to send in these microwave pulses from the room temperature all the way to where the qubit seated, right, which usually is at very, very low temperature, at like a sub 10 millikelvin stage. And you can imagine, right, analog signal sent through this require many, many components. For example, along the way, we need many filters, we need the attenuators, and when you read out the qubits, right, you need the multi-stage of the amplifications, right, in order to read signals. And of course, there's also space constraint, right? Because each qubit require like 1 to 2 cables in order to measure and control it. And if we are talking about like 100,000 or even million qubits, right, there's just not enough space, right? And also the heat generated is not acceptable, right? Because it will disturb qubit states. So our quantum architecture is very unique, right? Because we're trying to mimic what microelectronic industry was doing, right, in the past 40, 50 years, right? They are trying to create this like an integrated circuit type approach. So that means like we no longer rely on like individual cables, right, to send the signal to the qubits and read from the qubits. We're trying to build an integrated circuit, right, which can combine all this control and readout electronics on die, right, and integrate this kind of a control readout circuitry next to the qubits itself, right? So by doing that, don't need rely on that many cables, right, between room temperature and the millikelvin, because all the signal will direct generate right next to qubit, right? And then the signal will be read direct next to the qubits, right? So it provides huge benefits besides the real estate limitation, right? We can eliminate a lot of energy consumption, and also we eliminate the latency and the bandwidth issues, right? So it provides a huge advantage for scalability point of view and for energy efficient point of view.